Hello everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. So welcome to this lecture. In this lecture, we'll be discussing about binary codes. What do you mean by binary codes and what are the various types of binary codes we have? Weighted codes, non-weighted codes. What do you mean by weighted code, non-weighted code, and what are the basic differences between weighted and non-weighted codes? And various types of weighted and non-weighted codes we'll see. And in non-weighted codes, we have various types like gray code, XS3 code. So what is this gray code and XS3 code we'll be looking at, and BCD codes. These BCD codes are the examples of weighted codes. So we'll be discussing about BCD codes and how to perform some arithmetic operations on BCD codes. So that also we'll discuss in this lecture. So first of all, let us see what is a binary code. So the binary, already you know that in digital systems, we always use digital data, that is binary data, which is in terms of binary ones and zeros. So the digital data is represented, stored and transmitted as group of binary bits. This group is also called as binary code. That means whenever we are sending the digital information, it will be transmitted as a group of binary bits. So that group of binary bits is also called as a binary code. That means we can define the binary codes as a group of binary bits. So the binary code is represented by the number as well as alphanumeric letter also. So we can also represent this binary codes in binary as a number or as a alphanumeric letter. So the advantages of binary codes, why we need to go for binary codes, why we need to group the binary bits while transmitting. So binary codes are suitable for computer applications and binary codes are suitable for digital communication. So whenever we are transmitting the data, digital data from transmitter to the receiver, so we'll be grouping the information in order to reduce the storage required. Okay, so that is why we are going for binary codes. And binary codes make analysis and designing of digital circuits easy if we use the binary codes. So that means these binary codes makes the analysis and design of digital circuits easy. Next, the last advantage of binary codes is, since only zeros and ones are being used, implementation becomes very easy. So these are the advantages of binary codes. Now coming to the classification of binary codes. How can we classify the binary codes? So the binary codes are basically classified into following four categories. Those are weighted codes, non-weighted codes, binary coded decimal codes, alphanumeric codes, error detecting and error correcting codes. So these are the various types of binary codes here: weighted, non-weighted, BCD, alphanumeric codes, error detecting and error correcting codes. First of all, let us see what do you mean by weighted code. So the weighted codes are those that they obey the positional weighing system, or else positional weighing principle, which states that the position of each number represent a specific weight. That means each digit in a code will have its own specific weight. So that is the meaning of positional weighing principle. So the weighted codes or the codes which obey the weighing, that is positional weighing principle. What do you mean by positional weighing principle? Each and every number or else digit represents a specific weight. In these codes, each decimal digit is represented by a group of 4 bits. A group of 4 bits. That means we will be grouping the binary information into 4 groups each. So in these weighted codes, each decimal digit is represented by a group of 4 bits. So the weighted codes, each digit is assigned a specific weight according to its position. For example, in 8421, so the 8421 code is a weighted code where 8421 represents the weights of the corresponding bit positions. And this 8421 code is also known as BCD code. What is BCD? Binary coded decimal. So what is the equivalent of this 1001? So 1001. So according to 8421 code, so this is the positional weight of this bit is 1. This is 2, 4, 8. So that is 8 into 1, 8 plus 1 into 1, 1. So that is the total. The weight of the equivalent of decimal equivalent of this one is 9. So weights of 1101 from left to right will be 84 and 21 respectively. So that means in a weighted code, each and every digit will have its own positional weight. So here this is an example of weighted code 8421. One more example is also there, that is 2421 code is also an example of weighted code. Not only 2421, even we can have a 5421 like that. Positional, where in this 5421, these are the bit positions 0, 1, 2, 3. So that is the MSB is having a weight of 5, whereas the next bit is having a weight of 4, and the next bit is having a weight of 2, and LSB is having a weight of 1. So weighted codes will have positional weight for each and every bit position. So the examples of weighted codes are 8421, where the positional weights are 8, 4, 2, 1. So that is LSB is having a weight of 1, where MSB is having a weight of 8 and 4, 2, 1 respectively. And 2421 is also another example where 2 is a weight of MSB and 1 is a weight of LSB. So based on this weights, we can write the binary codes for everything. So for example, let us see 2421 code. So here the decimal digits here, decimal digits, let us consider 0, 1, 2, 3, 4, 5, 6, 7, 8, and maximum value that we can represent with 2421. Just a second. 2421 code. So here, what is the maximum value that we can represent all ones is 2 plus 4, 6, 6 plus 2, 8, 8 plus 1, 9. So that is 9. Okay. So 0 can be represented as 0, 0, 0 using 2421 code. 1 can be represented as 0, 0, 1. Next, 2 can be represented either as 1, 0, 0, 0, or else we can also represent this as 0, 1, 0, 0, 1, 0. And 3 can be represented as 0, 0, 1, 1. Next, 4 can be represented as 0, 1, 0, 0. And 5 can be represented as 0, 1, 0, 1. And 6 can be represented as 0, 1, 1, 0. 7 can be represented as 0, 1, 1, 1. Now 8. So 8 can be represented. How can we represent the 8? So 1, 1, 1, 0. Whereas 9 can be represented as all ones. So these are the 2421 codes for the decimal digits from 0 to 9. So like that, depending on the positional weights, we can write the codes for any decimal number that is from 0 to 9 or 0 to 15. But here the maximum possible value that we can represent, decimal value that we can represent using 2421 code is 9. Okay. So that is how we can, depending on the positional weights, we can derive the weighted codes. Now coming to the non-weighted codes. So as we have seen weighted codes, each and every bit position will have a positional weight. And here, whereas non-weighted code, as the name itself indicating, non-weighted codes are not positionally weighted. Means there is no positional weights available in non-weighted codes. That means, in other words, codes that are not assigned with any weight to each digit position are said to be non-weighted codes. The examples of non-weighted codes are XS3 code and gray code. XS3 code and gray code. So these are the non-weighted codes where we don't have any positional weights here. So here, now coming to the XS3 code and gray code. So XS3 code. So as the name itself indicates, first let us see the XS3 code. So XS3 code is also known as, in short, we can also call it as XS3 code. So why it is called as XS3? So the XS3 code words are derived from the 8421 BCD code by adding 3 to the by adding binary value 0011 or else the decimal value 3 to each code word in 8421. So that means the XS3 code words can be obtained by adding 3 to the decimal number or else 0011 to the BCD code. We can get the XS3 code. So that is why we are adding 3 in extra. So that is why we call this XS3 code. We call this code as XS3 code. So that is decimal number. First we need to get the 8421 BCD code. So how can we write down the 8421 BCD code? Just write by using these weights 8421, we can represent 0 to 9 here. So these can be obtained. Once a BCD code is obtained, just add 0011. In decimal, it is equivalent to 3. So just add 3 to this BCD code so that you will be getting XS3 code. So here, now 0. What is the binary BCD code for? BCD code, as I already told you that BCD codes are nothing but 8421. So here BCD code and the BCD codes for 0 to 9 are given here. 000, 0001 for 1, 0010 for 2, 0011 3, 0100 it is 4, 1015, 1106, 111 7, 1000, this is 8, 1001 is 9. So these are the BCD codes. Now the respective XS3 code for decimal number 3 is obtained by adding 0011 to this 000. So if I add 0011 0011, so what I'll get here? 1 plus 0 1, 1 plus 0 1, 0 0. So that is, this is the XS3 code for decimal digit 3. Okay. Similarly, 1. So what is the XS3 code for the 1? So 0001 is the BCD code for 1. Now add 3 to it. 1 plus 1, 0 with a carry 1. 1 plus 1, 0 with a carry 1. So it is 1 and 0. So that is 0100 is the XS3 code. Now similarly, 3 plus 3, that is 6. So 0110 is the XS3 code for 3. 010, 4 is the 4 is the decimal digit and the BCD code. 4 plus 3 is 7. So 7 is represented in binary as 0111. And next 5 plus 3 8. 8 is represented as 100. 6 plus 3 9. 9 is represented as 1001. 7 plus 3 10. 10 in binary is represented as 1010. 8 plus 3 11. How can we represent 11 in binary? 1011. 1011. And 9 plus 3 12. 1100. So this is how you can get the XS3 code for any decimal number. Just add 3 to the decimal digit so that you will be getting the XS3 code. Now here coming to the next one, that is gray code. Gray code, how can we get the gray code? So what is a gray code? So gray code is also a non-weighted code. It is not an arithmetic code. Okay, so what do you mean by arithmetic code? It is not, we are not having any positional weights. And here we can also call this gray code as unit distance code. The other names for gray code are unit distance code and one more name is that is reflective code. Reflective code. Why this is so called? Why it is called as unit distance and why it is called as reflective code? We'll be looking into it. So here, this is the major example of non-weighted code. It is also called as unit distance code and reflective code. So it has a very special feature that only one bit will be changing each time the decimal number is incremented by 1. So that means in another way we can also say that the consecutive, or else each and every consecutive gray code will be deferred by only one bit position, and hence it is called as unit distance code. That is the meaning of this one. Only one bit change each time the decimal number is incremented. So as a decimal number is incremented, the gray code will be changed by only one bit position, and hence it is also known as unit distance code. So as only one bit changes at a time, the gray code is also called as unit distance code. And the gray code is also called as cyclic code, or else we can also call it as reflective code. Okay, we can also call it as reflective code. Why it is called as reflective code, we'll see. Gray code cannot be used for arithmetic operations. So this is the basic introduction about gray code. So how to construct an n-bit gray code? So an n-bit gray code can be generated recursively because we don't have any positional weights. So that is why we should have some procedure for constructing a gray code. So how to construct a gray code? So I want to construct an n-bit gray code. What is the procedure? An n-bit gray code can be generated recursively using reflect and prefix. I hope you know the meaning of reflect. Nothing but mirror image. Reflection means mirror image. So reflect and prefix method, which I'm going to explain here now. Generate the code for n is equals to 1 down to 0 and 1 code. Okay. So here take the previous code in sequence 0 and 1 and reverse the codes in the following list 0, 1, 1 and 0. Now add prefix 0 for the original previous code and add prefix 1 for the new generated codes. So we'll be seeing this procedure so that you can understand. So first of all, I want to construct an 1-bit code. So n is equals to 1. When n is equals to 1, okay, so I want to construct a gray code for this. So here, first, n is equals to 1 means it may be either 0 or 1. It may be either 0 or 1. This is the 1-bit gray code, right? 0, 1. Now coming to the, when n is equals to 2. N is equals to 2. How many codes we may get? 2 per n. That is 2 per 2 is 4 codes I may get. So how to get the 2-bit gray code for that? How to get the 2-bit gray code for that? So first of all, write down the 1-bit gray code, which is 0, 1. This is n is equals to 1. Now I want to develop the gray code for n is equals to 2 by taking here, take the previous code in sequence. What is the previous code here? N is equals to 1 is the previous code for the n is equals to 2. So what is the gray code for n is equals to 1? That is 0, 1. Then take the next, what is the next step here? Add reversed codes in the following list. Add reversed codes. So if I put a mirror here, what is the reflection I'll get? I'll get 1 first and then 0. Now add prefix to the first previous codes with 0 and next previous code, next codes with 1. So first what we need to do? We need to take the previous code, previous gray code, where for n is equals to 2, what is the previous gray code? For n is equals to 1. So n is equals to 1, the gray code is 0, 1. So just take 0, 1 and take the mirror image or else reflection of that, that is 1, 0, and add prefix 0 to the first 2, that is original codes, and then 1 to the reflected codes. So here these are the reflected codes, and I'm adding prefix as 1 here. Now let us try to write n is equals to 3. So for writing the gray code for n is equals to 3, take the previous gray code. What is the previous gray code for n is equals to 3? N is equals to 2 gray code is the previous code. Just take the previous code 0, 0, 0, 1, 1, 1, 1, 0. And now take the mirror image of this. So if I take the mirror image, I'll get 1, 0 first, 1, 1 next, 0, 1 next, 0, 0. Now for the first original previous codes, add prefix as 0, and the reflected codes add the prefix as 1. So these are the gray codes for the n is equals to 3. So similarly, you can also write for n is equals to 4. So for n is equals to 4, you need to take this, and then you need to take the mirror image. Mirror image means 1, 0, 0, you'll get 1, 0, 1. So let us try to write this. So I'm taking n is equals to 3, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, next 1, 0, 1, 1, 0, 0. Now I'm taking the mirror image. If I take the mirror image, 1, 0, 0 first, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0. Now these are 8, 1, 2, 3, 4, 5, 6, 7, 8. First 8 previous codes add prefix as 0, and the reflected 8, 1, 2, 3, 4, 5, 6, 7, 8. So for the reflected 8 previous codes, you have to add prefix as 1. So this is the 4-bit gray code. So as we are using the reflection property, so we are also calling this gray code as reflective code. Okay. So that is the gray code. So these are the gray codes. So these are the binary. This is the table which is showing the difference between the binary code and gray code. So these are the binary codes, and the gray code is this one, and the 2-bit binary code is 00, 01, 10, 11. Whereas the gray code is 00, 01, 11 first and 10 next. Next 3-bit 000, 001, 010, 011, 100, 101, 110, 111. So these are the corresponding or else respective gray code for the binary code here. So 000, 001, 011, 010, 110, 111, 101, 100. So that is, you can observe the difference between binary code and gray code. So this is how we can construct any bit gray code by using the reflective property. So there is another way also. So this is the binary code, gray code, and this is the binary code. So we, as we have already seen the 4-bit gray code, how to generate 4-bit gray code. So we can also generate the gray code using a logic gate which is called as exclusive OR gate. So we already know the principle of exclusive OR gate. So the output of exclusive OR gate is 1 when both the inputs are different, and the output is equals to 0 when both the inputs are equal to when both the inputs are same. So this is the truth table. So x, y are the inputs and z is the output. So when both the inputs are same, that is 0, 0, the XOR output is 0. When both the inputs are same, that is 1, 1, also the output is 0. When both the inputs are different, that is 0, 1 or 1, 0, the output of XOR gate is 1. So this is the symbol for XOR gate, X, Y, Z. We can also represent this as Z is equals to X XOR Y, or else we can also represent this as X bar Y plus X Y bar. So this is the exclusive OR gate. Okay. So using this exclusive OR operation also, we can generate the gray codes here. Okay. So, and one more thing I forgot to tell you. So as I told you that this gray code is also known as unit distance code. Why it is so called? Because two consecutive, when a number is increment, what is the decimal equivalent of this? 0, 1, 2, 3, 4, 5, 6, 7, right? When the decimal value is incremented by 1, the gray code is changed by this. So how many bit positions are differed here? 1 bit. Now from 1 to 2. So how many bit positions are changed? This 1 is common, 0 is common. Only this value is changed. And from 3 to 2 to, from 2 to 3, that means the decimal value is incremented by 1. Now, gray code, if you observe, 0, 1, 1 and 0, 1, 0. So, how many bit positions is differed? It is differed by only 1 bit position. Next, like that, you can check any 2 consecutive codes. So, if 4 and 5 incremented by 1, so the gray code is 1, 1, 0, 1, 1, 1. So, how many bit positions it is differed? Only 1 bit. So that is why we can also call this as unit distance code. Any 2 consecutive codes will be differed by only 1 bit position. So that is why the gray code is also known as unit distance code. You may have a doubt whether the binary code is unit distance or not. So if you check it here, 0, 0, 0, 1, 0, 1, 0. How many bit positions it is differed? It is 2. Okay. So that is why it is not called as unit distance code. Only gray code is called as a unit distance code. So even if you consider this, so how many bit positions? Here it is 1. Now here if you see how many bit positions are differed, this is changing and this is also changing. So like that, the distance between 2 consecutive codes is not uniform in a binary, whereas it is uniform and it is equal to 1 in gray code. So that is why it is called as unit distance code. Okay. So now as I told you that exclusive OR gate is also used to convert a given binary code into gray code. So whatever it may be the number of bits in the binary, you can easily generate the equivalent gray code by performing or else by using the exclusive OR logic. So here we have a binary code which is of 4 bits here, B3, B2, B1 and B0, where B3 is the MSB and B0 is the LSB. Now I want to generate the equivalent gray code for this one. So the MSB in binary is equivalent to the MSB in gray code. So that is why we can directly take B3 as MSB of gray code. And now we can generate the next bit in the gray code by taking the exclusive OR operation of these 2 bits. That is B3 XOR B2 will give you G2. And similarly, B2 XOR B1 will give you G1. And B1 XOR B0 will give you G0. So that means I can simply write G3 is equals to B3 and G2 is equals to B3 XOR B2 and G1 is equals to B2 XOR B1 and G0 is equals to B1 XOR B0. Where B0 to B3 are the binary code and the equivalent gray code will be G3, G2, G1, G0. This is the equivalent gray code. So, this can be performed by using XOR gate. So, here now let us see. So, we have a binary code 1010. This is my binary code. Now, I want to generate the equivalent gray code for this one using that XOR logic. So, as I told you that MSB is same and the XOR of these 2, 1 XOR 0 is 1, 0 XOR 1 is 1 and 1 XOR 0 is 1. So, 4 ones is the gray code. So, here if you observe, this is the binary code and the equivalent gray code for this is 4 ones. Now, let us consider 0, 1, 1 is my binary code. Okay. Now, let us try to find out the equivalent gray code for this one. So, what is MSB? MSB is 0. 0 XOR 1 is 1 and 1 XOR 1 is 0. 1 XOR 1 is also 0. So, that is for 0, 111, the gray code is 0, 1, 0, 0. So, like that, you can find out the gray code for any number of bits. So, for example, let us consider a 6-bit binary number. Okay. So, this is my 6-bit binary number. Now, I want to find out the gray code for this one. So, how can I find out? MSB is same. Now coming to 1 XOR 1, 0, 1 XOR 1, 0, 1 XOR 0, 1, 0 XOR 1, 1, 1 XOR 1, 0. So this is the equivalent gray code. So what you can observe from this? So the binary code is 6-bit, whereas the gray code is also 6-bit. That means the number of bits in the binary and gray code are equal. Okay. So this is gray code. Similarly, even we can convert gray to binary also using this. The reverse operation also we can perform using the XOR logic gate. So what is that? How can we do that? How can we generate a binary code from the gray code? So here, this is a gray code which is having the 4 bits which are represented as G3, G2, G1, G0. And the equivalent binary number, a binary code is B3, B2, B1, B0. So here also we are performing the XOR operation, but in different fashion. So the MSB in both the cases, MSB is same. So the MSB of gray code is taken as the MSB of binary code, whereas B3 XOR with G2 will give you B2. Next, similarly, B2 XOR with G1 will give you B1. And B1 XOR with G0 will give you B0. So that means I can write B3 is equals to G3. Next, B2 can be obtained as G3 XOR, B3 XOR G2, and similarly B1 can be written as B2 XOR G1, and B0 can be obtained as B1 XOR G0. B1 XOR G0. So this is the formulation of gray code for the binary code from the gray code. For example, now let us have a binary code gray code. This is my gray code. Now I want to generate the binary code using applying the principle here. MSB is same 1. So 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. So 1 1 0 is the binary code. So 1 0 1 0. So 1 1 0 is the 1 1 0 0 is the binary code for the given gray code. So similarly, we can also find the gray code for the. So for example, we have a gray code 1 0 1 0 0 1 1 0 0 1 0 0 1 1 0. So this is my gray code. Now I want to find out the binary code for this one. MSB is same. Now 1 XOR 0 1, 1 XOR 0 1, 1 XOR 1 0, 0 XOR 1 1, and 1 XOR 0 1. Okay. So here already we have taken 1 1 0 1 1. Then we have got the gray code as this. Now if I take this, I'll be getting the reverse operation. I'll be getting 1 1 0 1 1, 1 1 0 1 1. This is my binary code. So like that, you can find out the binary gray code from the binary code, and similarly binary code if gray code is given. So in both the cases, the number of bits in binary and gray code will be equal. So this is about binary to gray and gray to binary, which can be performed or else which can be obtained using exclusive OR gates. Now let us see the binary coded decimal, which comes under weighted code. So binary coded decimal or BCD, what it stands for? What does it mean? BCD is that number system or code which has the binary numbers or digits to represent decimal number. So what are the decimal numbers we have? 0 to 9. So we will be coding this 0 to 9 into binary. So that is why we are calling this as binary coded decimal. Only the decimal numbers, decimal digits 0 to 9 will be coded into binary, and hence it is called as BCD or else binary coded decimal. A decimal number containing 10 digits, that is 10 digits, 0 to 9. In case of BCD, the binary number formed by 4-bit binary will be the equivalent code for the given decimal digits. Okay. And in BCD, we can use the binary numbers 0002 1001 only, which are the decimal equivalents of 0 to 9. Whereas we have, actually, if you take a 4-bit binary number, totally how many combinations we can have? 16. But how many we are representing? We are representing only 10. And that 10 are also varying from 0002 to 1001. So what about the remaining combination? What are the remaining combination? 1010 to 4 ones. So these combinations are unspecified in BCD. Unspecified combinations in BCD. Suppose if a number we have single decimal digit, then its equivalent binary coded decimal will be the respective 4-bit binary four binary digits of that decimal number. If the number contains 2 decimal numbers, then how can we obtain the BCD? Each decimal digit should be replaced by 4-bit equivalent binary, so that you can get the equivalent BCD code for a decimal number which is having more than 1 digits. Okay, for the first decimal digit and the next 4 for the first decimal digit, and the next 4 for the second decimal digit. So it may be declared, it may be cleared if we have an example. So for example, we have decimal numbers 0 to 15 here. Okay, and the respective binary numbers here 00001 and so on up to 4 ones. Now I will be writing the BCD code. I hope you can understand the difference between binary number and binary coded decimal. Only decimal digits from 0 to 9 are going to be coded into binary using this BCD code. So here the remaining 6 are all said to be unspecified combinations. So here we have listed 16 combinations of binary here, and now we are going to write down the BCD code. As I told you that if we have more than 1 digit in the decimal, so each digit should be replaced with its 4-bit BCD code. So here these are the BCD codes. So 0001, 0010, 0010, 0011, 0011, 0100, 0100, 0101, 0101, 0110, 0110, 0111, 0111. Right? So coming to the 8, 100, 100, 101, 101. This is the BCD code and binary code for decimal digit 9. Now from 10. 10 in binary is represented as 1010. Whereas in BCD, we have to represent 1 as a 4-bit binary group and 0 as a 4-bit binary group separately. So 0001 represents the decimal number, decimal digit 1, and 0000 represents the decimal digit 0. So this is the BCD code for decimal number 10. Similarly, 11. So 0001, 0001. This is the BCD code for 11. 12, 0001, 0010. Whereas the binary equivalent is 1100. Next, 001, 0001, 0011. This is for 13, where 13 in binary is represented as 110. Next, 14 in binary is represented as 1110, whereas in BCD it is represented as 0001, 0100. Next, 15, 1111, wherein it is BCD it is represented as 0001, 0101. So this is the way to write binary code. Sorry, BCD code. For example, we have 125. Decimal number. Now I want to get the BCD code for this. So the BCD code will be 0001. This is for binary. This is for the 1. 0010, 0101. This is the BCD code. Now if you want to write it in binary, so how can we write it in binary? So 2 6 2 4 2 2 so to 124, it is 1. Next 2 30s so 1. So 2 31s are 0. Next 2 15s are 30 and the remainder is 1. 7s are 14 and the remainder is 1. 2 3s are 6 and the remainder is 1. 2 ones are 2 and the remainder is 1. 2 0 1. So that is 1 1. How many ones? 5 ones. 5 ones 0 1. So what is the binary equivalent here? What is the positional value? 1 2 4 5 6 7 8. Okay. So 32 64. Sorry, it is 0. It is 0. Sorry, it is 1. So 0, this is 1 actually. 1. So 0, 1, 2, 3, 4, 5, 6. So 2 per 6 is 64. 2 per 5 is 32, 16, 8, and it is 4 and it is 1. So 64 plus 16, how much? 80. 80 plus 8, 88, 90, 90 plus 30, 90 plus 30 is 120, 120 plus 4, 124 plus 1, 125. So this is the binary code, whereas the BCD code is having how many digits here? It is 12. Whereas the binary code 1, 0, 1, 2, 3, 4, 5, 6, 7 bits. So this is about the difference between binary code and BCD code. So how many digit decimal number it is? The BCD code can be obtained by replacing each decimal digit by 4-bit binary equivalent, so that you can get the BCD code for the given decimal number. So we can also perform additions and subtraction of a decimal number using BCD codes. So BCD addition. So we'll be having some procedure for this. So first we will look into the procedure for performing the addition, BCD addition. So it is individually. So in this we'll be adding the numbers individually, the digits individually. It is individually adding the corresponding digits of the decimal numbers expressed in 4-bit binary groups, starting from least significant digit to the most significant digit. So that means first we can perform the decimal addition by using BCD also. So how can we perform the decimal addition? First we need to represent the decimal number in BCD code, and we need to start from least significant digit, and each 4-bit group is added, and if a carry is generated, that carry will be forwarded to the next group. Okay, so like that the addition will be done in group by group, starting from least significant digit to the most significant digit. If there is no carry and the sum term is not an illegal code, sum term is, so here we have seen that we are using only up to 1001. What about these 6 combination, that is 1010, 1011, 1100, 1101, 1110, 1111. So these are unspecified combinations in case of BCD code. Only 0000, 1001 are used in BCD, whereas 10102, 1111 are unused, or else we can also say it as unspecified. So if there is any illegal BCD code, that means if the sum is the result which is any one code of these 6, then it is said to be an illegal BCD code. And if an illegal BCD code has resulted, then we need to make some correction. What is the correction that we need to make? So if the carries, if the sum is an illegal code, then we need to add 6 to the sum. Okay, or else even though if there is a carry from one group to the other group, then also we need to add 6 to the group. If the sum is legal and if there is no carry, then when you no need to do any corrections. No correction is needed. Okay, so that is what the rules for performing the addition here. So the things you have to remember: first, get the BCD code for the given given decimal number, and perform the addition group by group, starting from least significant digit to the most significant digit. If the sum results a carry, okay, if the sum results a carry, or if the sum is an illegal code, then a 60110 is to be added to the sum. Okay, If no carry is resulted, and if there is no illegal code, then no correction is needed. Why we are adding 6? In order to make it legal, we are adding 6 to the result. So that is the procedure here. Now let us see. We have binary numbers. We are performing the BCD addition here. 0101, 0110. So now we are performing the addition. So 1 plus 0 is 1. 0 plus 1, 1. 1 plus 1, 0 with a carry 1. So, is there any carry? No. But the sum is an invalid BCD code because it is 1011. As it is an invalid BCD code, now add 6 to the result. What is the equivalent of 6011? 0. Add it. So, if I add it, 1 plus 0, 1. 1 plus 0, 1. 1 plus 1, 0 with a carry 1. 1 plus 1, 0 with a carry 1. 1 plus 1, 0 with a carry 1. So here, now, after converting the invalid BCD code into valid, so represent each 4-bit binary group by a corresponding decimal digit. So what is this? This is 1 and this is 1. So what is the result? Actually, what is this one? This is decimal equivalent 5, whereas this is 6. 6 plus 5 is 11. And the final answer is also 11. So this is how we can perform the addition. Now, example 2. Now let us take a BCD number 0001. 0001 is added to 0010, 0110. Okay. So now, here, we are adding these two by, we are performing the addition using BCD. So now, we are adding these two numbers, 1 plus 0, 1 is 1, 1, 0. Now 1, 1, 0, 0. So is there any illegal code? No, it is 3 and it is 7. Both are valid. So as both are valid here, no corrections are required. No corrections are required. So what is actually 1, 1 and this one is 2 plus 6. So how much it is? 7 and 3. 37. 37 is the answer. 37 is the answer. So 1, 1. Okay. And this one is 2, 6. 37. 1, 1 plus 2, 6 will give you 37. And finally the answer is here 37. Okay. So we need to, no need to add any 6 and all because both are valid codes. That is why we are not adding any 6 to the sum here. Okay, so this is about the BCD addition. Now let us go to the BCD subtraction. So BCD subtraction can be performed again by subtracting digits of each 4-bit group of the subtrahend. Okay, from the corresponding 4-bit groups of minuend in binary starting from LSD. If there is no borrow from the next group, then 6 is to be subtracted from the difference term. Okay, so that means here when I am performing the subtraction, if we are not taking a borrow from the next group, then no need to make any correction. Okay, if subtrahend, okay, if there is no borrow from the next group, then subtract 6 from the difference. So here, if there is no borrow from the next group, just subtract the 6 from the borrow difference. So now those are the rules. Okay, so if there is a borrow and if the difference is an illegal code, then no need to make any corrections, right? So now I'm performing the subtraction here. So that is one way, or else we can also perform the subtraction using even BCD subtraction using 9's complement subtraction and 10's complement subtraction. Okay, so now let us do this. So here, first of all, 31 minus 19. 1 plus 9, it is 10. Okay. 1 plus 9 is, it is subtraction, right? 11 minus 9, 2. And 2 minus 1 is 1. 12 is the answer. Right? So now I am performing the BCD subtraction. So here I can perform the subtraction using, now I want to perform the subtraction using this one. So first of all, I will be performing the subtraction using normal BCD. Okay, or a normal BCD subtraction I will perform. 31, 19, So here now I'm writing the BCD code for this. I'm writing the BCD code for this one also. 0011 0001 0001 1001. Now I'm performing the subtraction here. So 1 minus 1, 0, 0, 0 and 0 minus 1. Is it possible? No. We need to take borrow from the next group. So if I take the borrow, then it becomes 1. Now, here as it has given this 1, so it is 0 now. Again 0 minus 1. So it is not possible. So I am taking borrow from this. So what it will become? 2 minus 1, it is 1. Okay. And it is 0 minus 0, 0, 0, 0. So now, as I told you that, so just look at the, if there is no borrow from the next group, then 6 is to be subtracted from the difference. So did we take any borrow here? We did not take any borrow. We did not take any borrow here. So now, so there is no if there is no borrow from the next group, then 6 is to be subtracted from the difference. 6 is to be subtracted from the difference. So now, if I take this one, so what is the answer we are getting? 31 minus 19. So how much I have to get? It is 12 I have to get. So did I get 12 here? No, it is 8. Okay, it is 8. So that is why if there is a borrow, then we need to add 6 to the group. So then what I'll get? 0, 1. So we need to subtract 6 from the group here. 0 and this is 0, 1 and here we'll get 1, 0. So 2 minus 1, it is 1. 1 minus 1, it is 0 and it is 0. Now 1, 0, 0, 0. So how much is the answer? 1, 2. 12 is the answer. Okay, 12 is the answer. So this is how you can perform the subtraction. And now we can also perform the subtraction using tens complement and nines complement also. Tens complement. So what is a tens complement of? So whenever you are performing the subtraction using tens complement, first get the tens complement of subtrahend. Okay. So that is 19's tens complement. Okay. 19's tens complement is 9's complement plus 1. What is the 9's complement of this one? 99 minus 19. So 80. 80 is the 9's complement plus 1. So 81. So this is the tens complement of 19. Okay. Now, so we have got the tens complement here. And now BCD code I am writing 0011 0001 and 8 is represented as 100 and 1 is represented as 001. So as we have obtained the complement, now we can perform the addition here. So 1 plus 1 0 with a carry 1. So it is 1 and 0 0. Now 1 plus 0 1, 1 plus 0 1, 0 plus 0 0, 1 plus 1, 1 plus 0 plus 1 1. So now here, now if you look at this one, this is a valid BCD code, whereas this is invalid BCD code. If it is invalid BCD code and we are performing the addition, so then what we need to do? We need to add the 6. So if I add 6, what I'll get? 1, 1 plus 1, 0 with a 0 with a carry 1. 1 plus 1, 0 with a carry 1. And here 1 plus 1, 0 with a carry 1. As we are performing the subtraction using R's complement, this carry, if carry is generated, just ignore the carry. So just ignore the carry. Then the result will be considered as positive and the result is 1, 2. So this is by using tens complement. Even you can also perform the subtraction using nines complement too. Okay. So if a carry is generated in nines complement, just add it to the least significant bit. Now perform the decimal additions in 8421 code. 8421 code is BCD code. Right? First take A 25 plus 13. So what is the answer? 38. Now I am performing the BCD addition. So I want to write the BCD code for this one. 0010 0101. Right? 0001 0011. Now perform the addition here. 1 plus 1 0 with a carry 1. 1 plus 1 0 with a carry 1. 0 with a carry 1 1. Now 1 1 0 0. So is there any invalid code, invalid BCD codes? No. Is there any carry from one group to the other group? No. So that is why all these codes are invalid and there is no carry from one section to the other section. So no corrections are needed. And this one is represented as 3 and this one is represented as 8. This is the binary addition performed using BCD. Now coming to the second one, 679.6 plus 536.8. Now take 679.6, 536.8. Okay. So now 6 plus 8, that is 14. So now 10 plus 6, 16, 11, and this one is 12. This is the answer, 1216.4. So now I am getting the BCD code here. I should get the same answer here. 0011, 011, 1001.0110. Now 50101, 0011, 110.0100. Now I am performing the addition here. So 0, 1, 0 with the carry 1, 1. Now 1, 1, 1, 1. Now coming to this one, 0 with the carry 1, 1 with the carry 1, because 3 ones we have, 1 with the carry 1, 0 with the carry 1, 1. Now coming to this one, 0 with the carry 1, 0 with the carry 1, 0 with the carry 1. Now, do we have any illegal codes? Do we have a carry from one section to the other section? We don't have any carry from one section to the other section. But we have illegal code. This is an illegal code. Now make a correction. And this is also an illegal code. Make a correction. This is also an illegal code. Make a correction. Right? So now add. So now what happens? 0, 0 with the carry 1, 0 with the carry 1, 0 with the carry 1. 0 with the carry 1 now. Okay, sorry. Actually, I have taken wrong. 1, 0, 0. So then, just a second. So 0. Next to this one is 1, 1. 0 with the carry 1. 0 with the carry 1 now. We should be very careful while writing the codes here. 6 is represented as everything wrong. Okay. 6 is represented as 0, 1, 1, 0. 7 is 0, 1, 1. 9 is 1, 0, 0, 1. Okay. And 0.6, 0, 1, 1, 0. Next up, 0, 1, 0, 1. 0, 0, 1, 1. 0, 1, 1, 0. 1, 0, 0, 0. Right? So now add these 0, 1, 1, 1. Okay. Next up 1, 1, 1, 1. Next 0 with the carry 1, 1 with the carry 1, 0 with the carry 1, 1. Okay. Next up 1, 1, 0 with the carry 1, 1. So now all the codes are illegal. So now add 6 to all the codes. Add 6 to all the codes. 0, 0 with the carry 1, 1 with the carry 1, 0 with the carry 1. Okay. Now 0, 1, now 1, now 0, 1. Right. So now coming to this one, 1, 0 with the carry 1, now 0 with the carry 1, 0 with the carry 1. Now 0 with the carry 1, 1 with the carry 1. Okay. 1 with the carry 1, 0 with the carry 1, 0 with the carry 1. So now we have a carry. So this is a carry. So now we can write this one as 1. This is 2. This is 1. This is 6. And this is 4. That is the final answer is 1216.4. This is the addition, BCD addition. Okay. So next coming to perform, let us perform the subtraction using 8421 code, decimal BCD code, BCD subtraction. So now 305.5 and 168.8. So how much I'll get? 15 minus 8, it is 7. And this one is 9 and 10. 14 minus 8 is 6. Okay. And this one is, next, this one is 2 minus 1 is, so 9 minus 6 is 3, 136.7. So now, first, I want to perform the subtraction using 9's complement. Okay, what is the 9's complement of 168.8? So 999.9, 168.8. So it is 1, 3, and it is 8, 831.8. So 305.5, 831.5. This is the 9's complement. So now this is 6. Okay, and this one is 6, and this one is 3. This is 11. We have a carry. If we have a carry, just it is called as end around carry. Just add it to this 136.7. Now we'll perform this using BCD. Okay, so BCD. So what is the BCD code for 30011? And 0 is 0000. 0101 is BCD code for 5. Next, 8 is represented as 0100 0011. Next, 0001. Next, 0001. So this is BCD code for the numbers. 0 with a carry 1. This is 1. This is 1, 0. And this is 0 with a carry 1, 1, 1, 0. And this is 0011. 11, 0, 1. We don't have carry from one group to the other group. And this is valid, this is valid, this is valid. Only this is invalid. Now add 6. So the remaining all will be taken as it is. 1, 0 with the carry 1. So now the carry is added to the least significant digit. So what I'll get? 1, 1, 1. So finally the answer is 1, 3, 6, 7. 1, 3, 7. This is the final answer. So that means any way you can do, but the answer will be same. So we have performed by direct BCD subtraction. It is giving us the same result. Okay, 9's complement subtraction. It is giving the same result. And 9's complement BCD subtraction we are doing. So it is also giving the same answer. That means whatever the way you want to do, the answer should be same. So this is about binary codes, that is weighted codes, non-weighted codes, and what is XS3 code, gray code, and how to get the gray code from the binary and how to get a binary code from the gray code. And we have seen BCD arithmetic operations, how to perform BCD addition and BCD subtraction. Using complements also we have seen. I hope it is clear to you all. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.